whether a function is continuous or not. All right, Layman's definition of continuity, whether a function is continuous, is if you can graph it without picking your pencil up. Okay? No holes, no jumps, no vertical asymptotes. All right, the mathematical more rigorous definition is given there. A function is continuous at a number a if the limit of the function as x approaches a is the same thing as the y value, the function value at that a. All right, now couched in that definition, there's actually 3 parts to it. Okay, so 3 things you'll need to find/prove, all right, when you're trying to figure out whether a function is continuous. First off, is the function actually defined at that point? Can you plug that number in and get a value? All right, if you can't, it's not continuous. If you can, move on to the other 2. All right, second condition, all right, is that the limit must exist. All right, which I guess technically in that one, all right, is couched 2 other sub qualities that has to happen. All right, is that the limit of the function as x approaches a from the left has to be equal to the limit of the function as x approaches a from the right. All right, but that was what we had to figure out, whether if the limit existed. So that's hidden in there, but it's implied. All right, and then the last thing, if both the function exists and the limit exist, they have to be the same thing. They have to be equal to each other. And that third quality there, the third characteristic, is basically the definition. Okay, so it kind of encompasses all of it, but hidden in there, you got to make sure the function's defined, the limit exists, and if they do exist and it is defined, are they the same? All right, so the graph down here is a function that is continuous at this value of c. All right, you actually have a point there, and from the left and the right, you're both going to that point, and so they're equal, and it is continuous. All right, if you look at your next slide, all 4 of these graphs are not continuous. They're discontinuous. All right, but they're all discontinuous for different reasons. All right, the first graph is discontinuous. Why? All right, it's not defined at a. Okay, so this one's discontinuous. All right, because f of a is undefined. All right, and so if you're doing a problem, once you find it's not defined, there at that point, you don't have to do anything else. All right, but do notice the limit does exist. Okay, but it can't equal to the function because the function is not defined. All right, what about the one to the top right? Why is it not continuous? The limit doesn't exist. The limit of the function as x approaches a does not exist. Well. All right, and the reason why it doesn't exist is because the left limit, or the limit from the left, is not the same as the limit from the right. Coming from the left of a and from the right of a, I'm going to 2 different y values. So the limit doesn't exist. All right, what about the one at the bottom left? Yep. The function's defined, yes. There's an actual point there at a, f of a, but that's not the same thing as the limit. All All right, because up here, this point, there's your f of a. That y value is your f of a. All right, where this open circle, that's the limit. That y value there is the limit as you approach a. And they're not the same, so therefore it's not continuous. All right, and what about the bottom one here? Bottom right. All right, the limit doesn't exist. Or it's also, I guess it's all three of them. Okay? The function's not defined. All right, but at the same time, the limit doesn't exist. All right, if I was just asking the limit question, you could say infinity. All right, and technically you could say it here as well. All right, but remember, infinity and negative infinity as an answer to a limit is just a descriptive way of saying does not exist. All right, questions graphically there? Good. Finding answers on our phone. All right. Now, let's look at it when we don't have the graph. Okay? How can we tell whether a function is continuous at a point? Or I guess these questions are asking, where are they discontinuous? All right, where is a discontinuous? At 2. All right, this one is discontinuous. At x equals 2. All right, because f of 2 is undefined. If you just plug 2 in straight up, you get a 0 on bottom. You also get 0 on top, but as far as the undefined question, hey, it's 0 on the bottom. All right, and so yes, you could factor the top and cross some stuff out, but you can only do that inside the limit if you're actually trying to evaluate. All right, what about for b? Where is it discontinuous? If you said it, I heard something, but I didn't hear.
0.
At 0. This one's discontinuous at 0. All right, I'm defined at 0. All right, f of 0 is 1. That's what the bottom line gives us. All right, but the top, when I'm looking for the limit, I'm looking around 0, which would be the top part. All right, and that does not exist. It's going to infinity. Okay, so this one's discontinuous at x equals 0 because the limit of f of x as x approaches 0. And you could either write infinity or does not exist. All right, what about for c? All right, I'm guessing probably at 2 since the question asks where is it discontinuous. All right, but if I wanted to have a justification, all right, if I go through my 3 criteria for continuity, that's the word I was looking for earlier. F of 2 exists, it's what? 1. All right, but the limit of f of x as x approaches 2. All right, well, I got x minus 2 on the bottom. I could factor the numerator into x minus 2, x plus 1. And so the x minus 2's would cancel out. And so that would turn into the limit of x plus 1. All right, but by direct substitution, that's equal to 3, and they're not equal. Yeah. So since 1, which is your f of 2, is not the same thing as the limit of the function as x approaches 2, which is 3. All right, and so if I'm asking for justification on a problem, okay, if you show me this work up here, all right, if you show me what the function, where the function is defined, and you show me the limit, you could get away with just writing this little part right here, okay, because I've seen your work. All right, but another way to show your work is if you didn't show this up here, if you just did all that in your head, if you just wrote that long line of equal signs, that tells me you've done the work as well. Because I can say, hey, they found the function definition, it's 1. They found the limit, it's 3. And they've shown me they're not equal. Okay, if you're one of those who can just, hey, this is x plus 1, x minus 2, those are going to cancel out. All I got to do is plug it into the x plus 1. In your head, that's fine. Okay, but I would need to see those values somewhere. All right, what about D? What the heck is that? Anybody know? So louder. Kind of looks like it's an absolute value inside of a bracket or double brackets. Okay. This is a function, I think you might have seen it on that graphing card sort. Yep. This is called the greatest integer function. All right, that graph looks like a stair step. Okay. Also heard it called the floor function. All right, and so it can be written like this, or it could also be written, depending on the textbook, like this, where it looks like a bracket, but the top parts aren't there. All right, and so what it does, what the greatest integer function does is whatever number you plug in, okay, the output is the greatest integer that is less than or equal to the input. All right, that's our definition of a greatest integer function. All right, so if you're plugging in integers like 1, all right, the greatest integer function of 1, all right, that would just output a 1. All right, anytime you plug an integer in, you're going to get the integer out. All right, but if you plug in a decimal or a fraction, okay, or a square root number, but mainly we think about just like decimals and fractions. If I say, hey, what is the f of 1.73? All right, is 1.73 an integer? No. So you find the largest integer that's less than that, which would be 1. So it's kind of like rounding, except you're always rounding down.
Is it like if you're counting people or something?
Say again?
Is it like if you're counting people or something that you can't round up with?
Yeah, I guess. I mean, if you wanted to, like, what the average number of kids in a household is like 2.3 or something like that. Can't have a 0.3 of a person, so I mean it rounds down to 2. All right, and I believe on the next slide there you see, or 2 slides from now, you see the graph of that function there. All right, and so this one's discontinuous, okay, in a lot of places. All right, this one is discontinuous. Let me go back to it.
This for the stair step one?
So again?
This for the stair step problem?
Yeah. So the answer to this question, I gave you a lot of what the greatest integer function was because we hadn't seen it before. And I was kind of expecting that. It's kind of a weird function. All right, but this one's discontinuous at all integers. And I'll throw at all integers, I'll throw a letter up there, k. All right, so I can write because the limit of that stair step function, that greatest integer function, as x approaches k, does not exist. All right, because if you flip back over to that graph, which is on the next page for you, all right, when you go to the left and you come from the left and you come from the right of every integer, all right, so it's 0. As I come from 0 to the left, I'm down at -1. If I go from 0 to the right, I'm at 0. And so those limits don't exist because they're going to 2 different things for every single integer. Okay, I guess, I mean, another example of this, like, hey, how many cans of paint do I need to buy to paint a room?
That would be the opposite.
It would just be the opposite. I guess that would be a ceiling function. You'd need to what, round up every time? So the opposite would be like, how many cans do I need to paint a room? Well, hey, I only need 2.1 cans, but I can't buy 0.1 of a can. So I've got to buy 3 of them. Okay, even if I add the extra 10% because I'm going to mess up and there's going to be paint on the floor and on my body and on my kids' feet and on the floor because they've walked all over the place. All right, now we can actually give names to different kind of discontinuities. All right, so the first 2 there, okay, we call these discontinuities removable. All right, they're removable because we can remove that discontinuity. Or another way, we can say we can plug that discontinuity up by redefining the function at just a single x value. Okay, or if there's multiple discontinuities of this type, at individual distinct x values. Yes?
So if there's multiple holes in the graph, it's still removable.
It still could be removable. Because I could have a hole up here and a hole down here. All right, but both of those discontinuities are removable because all I'd have to do is say, hey, let me redefine the function at this x value, and let me redefine the function at that x value.
So you can redefine the function at multiple x.
At multiple x values, but they just need to be at distinct x values. Okay, and we'll see the difference between a jump discontinuity in a second. All right, so I could actually rewrite this function, okay, to fix the continuity issue by saying, hey, this function, we'll turn it into a piecewise function, and we'll use x squared minus x minus 2 over x minus 2. All right, but we're only going to use that piece of the piecewise function if x is not 2. Because if x is not 2, that function totally works, and it gives me all the points on that line. All right, and then I would define the other part as 3 if x was equal to 2.
Because it's 3 on the y-axis.
Yeah, because the limit of the top one is 3 when I approach 2. we saw on that last problem there. And so if I redefine and say, hey, I want this blue line for everywhere except for at 2, okay, because there's a hole there. But this second part, I want to say, hey, at 2, let's fill in that gap. I'm now continuous. All right, and the same thing could happen on C. All right, because on this one, it's essentially the same function, but it's already piecewise. All right, the problem is we defined the function at 2 in a bad place. We find it where it's not the same thing as the limit. So this one I could fix by just changing that 1 to a 3, and we're good. All right, and so if you had multiple places there, if you could write a piecewise function just defining each of those values at those particular points, it's removable. We could fix that function. All right, on the next slide there on the bottom of your page, okay, we call this first discontinuity an infinite discontinuity. All right, and this is going to happen when you have vertical asymptotes. All right, when your limits are going to infinity or negative infinity. All right. So whether this bottom part of the piecewise function was there or not, this has an infinite discontinuity because, hey, we have a problem at 0, all right, but there's no way, since these keep on going up for forever and never actually getting to 0, the x value of 0, there's no way to bridge that gap. There's always that line that it's not going to cross. All right, and then for the greatest integer function and other piecewise functions as well, all right, we call these jump discontinuities. Because if you're going from one part of the graph to the next, you have to jump to another place. All right, so there will be no way to fix this unless we took this whole section right here and we either shifted the whole thing for all the values between 0 and 1, either moved it up or like tilted it or something like that. Okay, so we wouldn't just be changing the values at 1, 2, 3, and 4. We'd be changing the values of all the numbers between 0 and 1. All right, which John Green taught us there's an infinite amount of numbers between 0 and 1. All right, and with that, we can't fix it. All right, one of the type questions that I'll ask, and the AP asks a lot, all right, is, hey, can we fix these discontinuities? Okay? All right, or can I fix this function so that it is continuous? So here I've got a piecewise function, all right? Up top, it's defined for everywhere except for at 1 as this function here. All right, and then at 1, we're defined at some value of a, and I want to pick the value of a that would make it continuous. All right, so I'm like on this last one over here, hey, I'm picking this value down here. I'm making it the number that would match up with the limit. All right, so what you would do on a problem like this is you say, all right, well, let me look at the limit of the top. All right, what is the limit of the function g of x as x approaches 1? All right, because we want the limit and the function defined to be exactly the same place, and so we got to find out what the limit is. All right, so if we factor the numerator, we would get x plus 3, x minus 1. Let me put my limit notation, my bad.
We need to have that in the work on right now.
Yeah. I know. It's annoying. All right, and since that numerator factors and one of those factors is what's in the denominator, inside the limit, the x minus 1 can cancel out. All right, and so if we were to plug 1 in now, you would just get what? 4? All right, and so we could find the value and say A has to be 4.
And so we're going to just put equals 4, and we also have to put limit for that too.
Now, once you evaluate it, once you plug in the number into it, use that direct substitution, you're done with the limit.
So the limit's just for the first step, where we like our
It-
pattern and stuff.
You're factoring in any kind of manipulation you're doing, like when you multiply by the conjugate on the limit problems that we had on the worksheet. Any kind of manipulation of the expression, you need to have the limit. But as soon as you plug the number in, you're done with that limit notation. All right, let's look at the bottom one here. All right, I got not one, all right, but I got two numbers I need to find, both A and B. All right, so we look at this piecewise function, we say, hey, what's happening on this piecewise function? I'm using this quadratic when I'm less than 1. I'm using this linear when I'm between 1 and 3, and I'm using this cubic when I'm greater than 3. Okay? Besides the fact that we have piecewise function, we're good everywhere on this x squared. A polynomial is continuous everywhere. It's defined. So is a line, so is a cubic function. So the only places we need to look for those discontinuities are where the pieces match up. Okay, so first thing we would need to look at is we'd have to compare what's the limit of this function at the first place that the pieces meet, which would be what x value? 1. So we need to look at the limit from the left, and we need to look at the limit from the right. All right, so from the left, which piece of the piecewise function would we be using? The first one? All right, so if I were to plug in, well, I'll do that in a second. So I'm using the 3x squared plus ax minus 2. All right, and from the right, which part of the piecewise function am I using? Second part, the 5x plus 4. All right, which you could have not written this first step and just gone straight to here, and I'm good with that. All right, you do notice that I'll put parentheses around what's inside the limit if there's more than one term. All right, because if I didn't have parentheses around that 5x plus 4, all right, was that the limit of 5x and then plus 4, or is that the limit of the whole thing? Okay, so I do put parentheses if there's more than one term in there. All right, on both of those, you can do direct substitution. All right, so you get 3 plus 1a minus 2. If you plugged 1 into the right side, you ended up getting 5 plus 4, which if you went straight to the numbers, 9, that's fine. So this would be a plus 1 is equal to 9. All right, and so to make it continuous between the one less than 1 and between 1 and 3 parts, a would need to be 8. All right, and then the b part, to find out what the b is, you would need to find the limit as x approaches 3 from the left, which is the 5x plus 4 part. And you need that to be the same thing as the limit as x approaches 3 from the right, which is the bx to the third part. All right, if you plug 3 in there, you would get 19 on the left-hand side. And you get 27b on the right-hand side. And so in order to make this continuous, you would need to have the b to be 19 over 27. All right, questions on that? All right, so graphically what's happening there? What? No, so just to see graphically, this is what we got going on. All right, here's the 3 different pieces. All right, but I've made A just whatever I wanted it to be, and I made B whatever I wanted it to be. So if I were to slide A, okay, that's making the left side of this function kind of tilt a little bit. Okay, so we need to find the A value that makes that match up. All right, which we said was what, 8?
Yeah.
So if I turn that to 8, that purple part there meets up with the red part. All right, and the B, I need to get it where the blue part meets the red part, and so moving the B around would change where that cubic is. So I needed to match it up perfectly. All right, and then 0.7, which is probably close enough to 19 over 27 that graphically we can't tell. Okay? That's what we're doing. All right, try this one. All right, what do we get? You got the what? All right, square root of 5. Anybody else get square root of 5? All right. It's kind of a troll question. There's not a value here that works. All right, because if you were to work it out, and hopefully I did all my work correctly here. All right, you get negative 5 is equal to a squared. Okay, because that when you plug the -1 in for x, they'll start turning into negative a squared, but only the a's being squared. So if you divide that out, and at that step, if you were to take the square root, you're taking the square root of a what? Negative number, which turns into, it'd be I squared roots of 5, positive or negative. All right, which is not a real number, so there's nothing we can plug in real that will make that work.
Are we going to use I?
Yeah, we're gonna win.
In calculus, we're just going to talk about the real numbers. We won't talk about imaginary numbers and complex numbers in calculus. Or at least not the calculus we'll learn here in high school. There are some calculuses that extend into the complex numbers, but not for us. All right, let's take a quick little break. About 5 minutes or so, just kind of give your ears a rest from listening to my lovely voice.
Very